Hello, good afternoon. Reese, how are you today? You have a good weekend? If you can hear me, can you please give me a smiley face, please? Thank you. Um, you you raised your hand. You have questions? Um, I hope you have a good weekend. Please take a moment to input your idea about the warm-up questions. What is the difference between Euler path and Hamilton path? Today, we will review Euler and Hamilton circuit and path. First, we want to understand what's the difference between path and circuits, and what's the difference between Hamilton and Euler circuit and path. And we will also look at minimum spanning trees. If we have more time, we will look at graph coloring. Okay, we've got time. Okay. You got it right. Euler goes to edges once, each and every edges once, and only once. Okay, only one time, no more than one. Hamilton goes to each vertex only once. But the both start and end at the same vertex, that applies to circuits, which we are going to look at. Okay, so for Euler and Hamilton circuit, instead of path, they will start and end at the same vertex. Okay, for if we talk about Euler or Hamilton path, then they can start and end at different vertex. Okay. So now we're gonna look at just a little quick review. Graph theory, you can download the PowerPoint at the bottom of this part. Today is July 5th, so find the July 5th graph theory PowerPoint and download it for yourself to keep. Alright, so first we need to kind of clear the definition and terms. When I use these terms, I want you to so that we are on the same page what that means. What is a loop? Okay, a loop is the edge that go back to the same vertex instead of going to the different vertex. At vertex number 4, there is a loop that going back to itself. What is the degree of vertex? We need to know the degree. So the blue knot here, we call it vertex. Okay? And if there's line coming out from a vertex, we call it edge. The number of edges that connected to each vertex, we call it degree. And this whole thing that we have here, we call it graph. Okay, this is a vertex H graph. Okay, so now let's look at any questions so far. No questions? Are you there with me? If you're there with me, just type a hi so that I know you're there. Okay. So now we're gonna review what's Euler and Hamilton path and circuit. For Euler path, the path goes through every edge of a graph exactly once and can start and end at a different vertex. If we talk about path, both Hamilton path and Euler path can start and end at different vertices. Euler circuit and Hamilton circuit, if we talk about circuit, it's like a circle, right? You have to start and end at the same vertex. Okay? The difference between Euler and Hamilton are, for Hamilton, like you just said, for Euler, like you just said, the graph goes through every edge of the graph exactly once. Whereas for Hamilton circuit, it goes through every vertex, start and end the same point exactly once. Okay? And here's the link you can study more about Euler and Hamilton path and circuits. Any questions so far? Okay, good. Alright, now we look at the theorem. In the discussion post, we are discussing a conjecture after we did the task to see, okay, so what is the quick way for me to tell whether this graph has the Euler circuit or not, or Euler path or not. Okay, and these are the Euler's theorem. Theorem means a conjecture that has been proved to be true. When we call it theorem, it's something you can just use it because it has been proved to be true. When we talk about just conjecture, just okay, I think this is true, but I still have to prove it. But when people call it a theorem, meaning it's already proven. So Euler's theorem number 1 says if a graph has any vertices of odd degree, then it cannot have an Euler circuit. So meaning it cannot have the Euler circuit that Euler circuit start and end at the same point. It cannot have that if it's any vertex of odd degree. And if the graph is connected and every vertex has an even degree, then it has at least one Euler circuit. Okay? If all the connected vertices has even degree, every vertex has even degree, then it has at least one Euler circuit. Sometime more. Okay, every vertex has to have even degree for that to happen. Theorem number 2. If a graph has more than 2 vertices of odd degree, if it has more than 2, then it cannot have an Euler path. Meaning it cannot have an Euler circuit either. If the graph is connected and has exactly 2 vertices of odd degree, but if it has only 2, then it has at least one Euler path. Sometime more. Any such path must start. Okay, this is a very important point. Start and end. Start. So if you have 2 odd degree, vertices, then to have the Euler path, you must start at one of the odd degree, and then you will end at the other odd degree vertex. That is the Euler path. Because the Euler path doesn't require us to start and end at the same vertex. Okay? But to have an Euler path, you must, if there is a graph that has two vertices of odd degree, then you must start at the one that's odd degree and end at the other odd degree one. Okay? But if you have more than two odd degrees vertexes, then there's no Euler path or circuits. Euler's theorem number 3. The sum of the degree of all vertices of a graph is an even number, exactly twice the number of edges in every graph. The number of vertices of odd degree must be even. Well, theorem number 3 is important, but it is not as important for this topic that we are discussing, for the question that you need to know. Okay, so let's look at this theorem summarized in a table. Meaning, if you are given a graph, okay, you want to know whether this graph has the Euler path or circuit or not. You will look at number of odd degrees vertices. First, you need to know how to count the degree correctly, and then only you can refer to this table. If the number of odd vertices is 0, then there is at least one Euler circuit, meaning all of the vertices is even number degree. Okay, 2, 4, 6, 8, and so on. Okay. If number of odd vertices is only 1, if there's only one, it's impossible for you to have either Euler circuit or Euler's path. If the odd degree vertices is 2, if you have 2, then there is no Euler circuit, but you can have one Euler path. Okay, no Euler circuit. You cannot start or end at the same point, but you can have one Euler path that starts at one of the odd degree, goes through all the edges, and end at a different odd degree vertex. Okay? If there's more than 2 odd degree vertex, and there will be no Euler circuit or Euler paths. Any questions regarding this table? Okay. Okay, good. Now we're gonna do some practice. This is the same. This is just redundant information. All right, let's look at some questions. Given these questions, how many Euler circuits can be found in a given graph? You're given a graph, and you know the theorem. So the first thing you do is to find the degree of each vertex. Okay? And then you compare with the information that we just learned. I give you a minute. Do you know how to find the degree of each vertex? Okay, so I give you a minute to try it out, and then you tell me what you think. Okay? The answer choices are here. 0, 1, 2, 3. The answer is 0. Why? Because look, these three vertices has odd degree, okay? They have odd degree in these three vertices. So according to the theorem, if there's more than two odd degree vertices, then there will be no Euler path or Euler circuit. Okay? Awesome. Now, look at these, compare these three graphs. Graph 1, 2, and 3. Okay? We want to see which one has Euler path and which one has Euler circuit, which one has Hamilton path, and which one has Hamilton circuit. For Hamilton, like you understood, Hamilton, you will pass through each and every vertex exactly once. You might not pass through each and every edge. Okay? This is applicable for postmen, okay, when they have to deliver mail to each and every house, but they don't have to go through each and every street. You know what I mean? But this is just, a real life application is much more complicated, but it is definitely an application of Hamilton when we talk about mail lady delivering mail. So looking at graph 1, let's look at whether this graph has Euler path or Euler circuit. It's the same thing, we'll look at the vertices. Yes. So you are gonna count vertex of the graph. I hope you have. If you count the vertex of the graph, okay, vertex A has 2 degree, vertex B is 4 degree, vertex C is 3 degree, vertex D is so vertex D. Here's the tricky part. If there's a loop, you count as 2. So how do you count? You just count how many lines connected to that vertex, right? So it's 1, 2, 3, 4, 5. So vertex D is 5 degree. Vertex E is 4 degree. 1, 2, 3, 4. Vertex F is 2 degree. And then you realize, oh, there are 2 vertices that are odd degree. So what do we conclude from here? So there are 2 odd degree vertices. So according to the theorem, there's no Euler circuit, but at least one Euler path. And where should I start my Euler path? Are you there working or calculating? Where should I start my Euler path? Or if you have questions, let me know. Well, if, okay, let me see, I can type it. Remember the theorem say, if there are two odd degree vertices, then to get the Euler path, you must start at one of the odd degree vertex and end the path at the other odd degree vertex. So you can either start at C and at D, or start at D and end at C. Did I clarify for you? It's the application of the theorem. We are not proving it here because proving takes a long time, because you have to use all kinds of circuits to prove that this is true for all different kinds of circuits. But this is already proven. If you have two odd degree vertices, then there's no Euler circuit, but at least one Euler path. To get to the Euler path, you must start at one of the odd degree vertices and then end at the other one. Okay? Alright, good. Now let's look at Hamilton path and Hamilton circuit. We need to draw a path that passes through each and every vertex, right? Exactly once. That's for a Hamilton path. Doesn't matter how it goes, as long you can start and for Hamilton path you can start and end at a different vertex. Whereas Hamilton circuit, you have to start and end at the same vertex. Okay? You don't have to go through each and every edge exactly once. You don't have to do that. So let's say for Hamilton path, this is how I would type my answer. Alright, for Hamilton path, I can have a Hamilton path. Example, I will start with vertex C. This is how I write my answer. C, D, B, E, F, A. Meaning I start with vertex C and I go to D. Then I go to B and then E and then F and then A. I pass through all of the vertices exactly once. Okay? Are you good with that so far? Just Hamilton path? Okay. Hamilton circuit, make sure you have to start and end at the same vertex. So I chose to go from A to B, B to C, C to D, D to E, F, and then I go back to A. There might be more than one of them. Okay, this is just one example. Okay, so you're good. Let's look at the second one. Right now, to see, this is graph 2. This is the second graph. We want to see whether this graph has Euler path or circuit. First, we'll count the degree of each graph. Can you count the degree? And once you're done, you can type the degree in the chat box. Say A equal to how many, B equal to how many, and then we will conclude it, whether it has Euler path or circuit. So, if we count the degree of each vertex, you will figure out A has 3 degrees, B is 4, 1, 2, 3, 4. C has 3 degrees, and D is 5 degrees, E is 4 degrees, F is 3 degrees, and G is 2. You say we have 4 vertices that have odd degree. There are 4 odd degree vertices. So, according to the theorem, if there's more than 2 odd degree vertices, there will be no Euler circuit or Euler path. No Euler circuit, no Euler path. Okay? And next, we want to see whether this graph has Hamilton path or circuit. So it has a Hamilton path. This is one example. A going to G, F, E, B, D, C. This is one Hamilton path. Okay? And here's a Hamilton circuit. You have to start and end at the same vertex. So I chose to do A, G, F, E, D, C, B, A. That's Hamilton circuit. Can you please give me one example of Hamilton path using this graph that's different than mine? No? There's another Hamilton. So I chose to do A, G, F, E, B, D, C. You can do Hamilton path starting at different vertex. You can do C, B, D, E, F, G, A. There'll be one Hamilton path. Or you can do, I don't know, E, D, C, B, A, G, F. That's another Hamilton path. For Hamilton circuit, I can start with D, a different Hamilton circuit, different than mine. D, C, B, A, G, F, E, back to D. Okay, so there are more than one choices that you can make. Okay, all right. So any further questions? We will do one more example because there are 3 graphs there. Okay, you're gonna try the next one to see whether this one has order path or circuit. First count the degree. Okay. I give you a minute to count the degree and then come up with your own conclusion. Okay, sorry. Can you please give me one example of Hamilton path? So start at A, B, C, B, C, G, D, E, F. And then this is, if you go back to A, that will be a Hamilton circuit. But if you add an F, there'll be Hamilton path. Good job. I have A, F, E, B, C, G, D. That's Hamilton path. And my Hamilton circuit, I have A, B, C, just about like yours, except I end at A, then I make it a circuit. Okay, if you circuit like a circle, you go back to the original starting point to make a circle. All right. So this is additional questions. So according to what we have known just now, if there's two vertices with odd degree, then there are the starting and the ending vertices for the Euler path. Okay? So I'm telling you this graph has an Euler path. But which vertex should the path start and end? Which vertex should the path start, and then which vertex should it end? Just one example. B. Okay, good. Then if it start at B, which one should it end? It's not in the choices. I'm asking you as the extensions of the question. So we have said start at B. If you start at B, which one would it end? If you know which one it will end, then when you try to figure out the circuit or path, then you know where you are heading to. Okay, so according to the theorem, okay, if there are, we know this one has two odd degree vertices because vertex B has 3 degree, 1, 2, 3, and vertex E has also 3 degree. The other vertices are all even number. So if it start at B, then it will end at E. It's Euler path. Euler path don't have to start and end at the same point. If you have only even one odd degree vertex, there will not be any Euler circuit. Okay, circuit sound like a circle. You start and end at the same point, but there's not going to be any Euler circuit here because there's one odd degree vertices. And here's another one, so 2 total. But we have Euler path. We can have Euler path which it must start at one of the odd degree vertex and end at the other odd degree vertex. So if you start at B, end at E. Start at E, end at B. Question? Yes. Let's see. So we want Euler path, so you only have to pass through each edge once. I'm figuring it out. Like, I don't know the answer. I'm just trying to figure out, but I know this must be 1. So can we go C, F, E, D, going to B, A, E. So, okay, I figure out 1. One that start at B and end at E. So going from B, what did I do? B, C, F, E, D, B, A, E. That's one Euler path. Start with B, end with E. Okay, let's start one with E. If I start with E, okay, can I do this? E, F, C, B. Okay, E, F, C, B, D, E, A, B. So I'll show you an example for both. Now, sometimes we get confused with, oh, I shouldn't touch each vertex twice, and then I cannot go there again, But this is not Hamilton. This is Euler. So Euler, as long you pass each edges one time, you can touch each vertices, multiple times. That is fine. Okay. This is applicable for street cleaning car. The street cleaning truck. They have to clean each and every street. Sometimes they just have to go through some junction a couple times to turn to a different street. Okay? This is how to say it? When you have the table with you, okay, you're welcome. When you have the table with you in a quiz or test, as long you count the vertex degree correctly, and then you applied it correctly according to the table, then it should be correct. The theorem has been proven, meaning you don't have to worry it's gonna be wrong if you count the degree correct and you applied it correctly. You understand? It's yeah. But now is the time for you to ask questions like you just did. Can you show me how? I said, yes, I can show you how for this one. Which is good. All right. Next part. This is part of the assignment in the content. Have you looked at this? Do you have any questions? If you have questions, I can answer. Otherwise, we can go to the next part. You haven't looked at this. Oh, hi, Rafi. Welcome. We are working on Euler's circuit and Euler's path. Happy to see you here. This is your first time. Yay! So this is an application of, let's see which one that we are trying to figure out. Let's read the questions. You're planning a trip around the world by visiting each city exactly once and using only identified routes to travel from city to city. The dashed lines represent routes on the opposite side of the globe. Okay, so I only want to visit each city once. I don't have to go through each path once, each edges once. So this is the application of Hamilton. Okay, so we can start anywhere. Where are you? Where do you want to start? We can start anywhere, and then we want to make sure that we what's it called? Travel each and every city. Okay? It doesn't say you have to start and end in the same city. So you can start and end in a different city. Okay? So you guys ready to try this out? We're just gonna come up with one route. Okay, I'm gonna type and you're gonna tell me what should I go next, okay? Alright, where should we start? Traveling. I love travel. I'm not sure about you. But I'm stuck right now. Okay. Paris. I love Paris. I'm gonna go there someday. After Paris, where should we go? Oh, somebody said London. Okay, let's close. Let's see. Where's Paris? Paris. If we start with Paris, then can we go to London next? Okay, we can go London next. Okay, Paris and then London. You see what I type? So we are going from Paris and then London, and then where else should we go? Fargo. Okay, that sounds great. Fargo. Okay, next. You guys can type. I'm just gonna create your path on the paper for you. It has to be connected to Fargo. You can go to Chicago or Fairbanks. So here's two choices. Fairbanks, okay. Okay, then where else should I go next? So in Fairbanks, you can go to Tokyo or Honolulu. Have you guys been to Honolulu? Yeah. I've been there in my dream. Never been there. Okay. So now Honolulu, we have two choices. Where should we go? San Francisco or Brisbane? I can do a video of field trip. Brisbane. Okay, Honolulu, Brisbane, then just keep typing. The faster you type, the faster I can enter the question answer here. After Brisbane is Hong Kong or Santiago? Hong Kong. Okay, you are flying to the east now. Okay. After Hong Kong, you can go to Tokyo or Madras. Tokyo is the most, is not probably not the most, but very, very dense city. You know, Tokyo is actually not a city. Moscow, okay. Next, you can go to, well, we've been to London, so the next thing is only have one choice, Istanbul. No, you cannot go to New York. No, Moscow doesn't have a path to New York. You look carefully. Is a dotted line Moscow connected to London or Istanbul? Okay. Okay, after Istanbul, you can go to, look at the dotted line now because we are on the other side of the world. We can go to Madrid or Madras. Have you been to Madras? Not yet. Madras. Okay, after Madras, we can go to, okay, well, we've been to Hong Kong, so we have to go to Cape Horn. That's the only choice. Then from Cape Horn, we have to either go to Santiago or Casablanca. Now go to Santiago, we have a choice to go to, well, we have to go to Tijuana because we've been to Brisbane. Okay, where's next? San Francisco. Haven't we been there? Not yet. You guys been to San Francisco? I have a, I've been there. They have one of the steepest street. Oh my goodness, steepest street. And the houses are small, the streets are very steep, and but it's beautiful. But it's foggy sometimes. Most of the time it's foggy. And they have a Chinatown, big Chinatown there. But it's a beautiful place. Wow. Next, Francisco going to Chicago. All right. Hope you enjoy your trip, Rafi. This Saturday you're going to Panama City Beach? New York, going back to New York. Have we been to New York yet? Not yet. Okay, then we can go to New York. Have we been to all the places? Not yet. We haven't been to all the places. I never been to Panama, but I heard it's beautiful. Well, you can, if you have computer there, you can do it there. Final exam it's not happening until Thursday, but Monday we have, last batch of work that need to be turned in. Tuesday I'll have review. But enjoy your trip. One day is not enough though. New York. All right, you must love it, otherwise you won't go back again. So after New York, where should we go? New Orleans, right? Casablanca. What's the last place we are going to? I think I want both of you to verify that we've been to all the city. Madrid. Okay. Verify we've been to all cities. So this is an application of Hamilton path. Okay. However, usually we have to do Hamilton circuit because usually you leave your home. Let's say we live in Atlanta. We leave Atlanta and go to wherever we're traveling. And then we come back to Atlanta because it's our home. Unless you're traveling around the world. But, if you have a home, you find eventually you still have to go back to it. All right. So you guys did a good job. You can start anywhere and you don't have to end at the same point. And this is just one example that I give. Any questions on here? Good. If you were to do the different path, you can figure it out, right? Good. So the next big topic that I'm going to talk about is minimum spanning trees. Okay, minimum spanning trees is okay. So first we need to know what is a weighted graph. Okay, a weighted graph. Now I want you all to pay attention to these questions. This information itself has a questions. In the test, they will just ask you, what is a weighted graph? Well, if you see a graph that we work on, Euler path or Hamilton path or circuit, if you see numbers on the edge, we call it a weighted graph. Because each edge represents certain values, okay, either big value or small values, okay? Meaning, for people who are, let's say, street cleaning car, right? The values on each edge could be the time that required to clean that street. The edge represents the street. So you need to have numbers on those edges for them to figure out what is the fastest time to clean this town, let's say. So that's what we call weighted graph. Now, surprisingly, from my past experience, many students didn't get this question correct. That's why I kind of pointed out. If you see numbers on the graph, they are not Euler path, they are not Euler circuits, it's not a path of circuits. They're just a weighted graph, a graph that have numbers. Just means they have value on each edge. Now, keeping all the vertices connected by a path. By a path, remember, it's not circuit, by a path, meaning you might start and end at different points. Okay? Keeping all the vertices connected by a path, resulting in minimum total weight, is called finding the minimum spanning tree. This is application like the street cleaning that I'm talking about. How can you clean? I guess this, if you want to find a minimum spanning tree, in this case will be, let's say, mail delivering. The shortest time to deliver all the mail to everybody. And you will find a minimum spanning tree. Okay? How do you think those postmen, mailmen figure out which house should go first? Right? They have this method. They use this method to figure it out. What we're studying is just the surface of it. There are more to it, okay? But this is just the surface. The word spanning means each vertex remains connected to the graph. So when you work on the minimum spanning tree, make sure each of the vertex is connected. As long as it's connected to one other vertex, it's good. Okay? And the word tree indicates if there's no cycles. If there's a cycles, then it's not a minimum spanning tree. Because you don't want to revisit the same house. You don't want to deliver the mail to the same house 2 times. If that's just example. Okay, so let's see what's next. So we will use Kruskal algorithm to figure out the minimum spanning tree. Roughly, for your information, this PowerPoint can be downloaded at the part below. Find July 5th graph and you can download that. Assume that you start with a table of weight associated with each edge. Put all the weight in a list from the smallest to largest. Well, here's the step. You can print it out using your printer. I think you'll be clearer when I show you the video that show you the example. Okay? I'm going to show you the video. You have paper, pencil to solve this problem. This is our graph, and C represents a vertex, and this represents an edge, and the number on the edge represents the weight of the graph. And this graph that you're looking at is a weighted graph. So to get to the minimum spanning tree, first remove all the loops. Any edge that starts and ends at the same vertex is a loop. Okay? Okay, loop is gone. Now, if you have a parallel edge between two vertices except the one with the least weight, you have to remove it. So between A and C, there are two choices. Okay, you want a minimum, so you keep the smallest number. So let's go back a little bit. Okay, so first you in the weighted graph, you go from the smallest number, smallest weight, you keep that one, okay? After you have the smallest weight, you go to the next smallest, okay, the next one up, and then you want to see whether this will make a circle. If you make a circle, you only keep one of them. So let's say BA and AC. You can keep the edge that connect BA or the one that connect AC. So just keep one. And then go up to the next smaller one, which is the edge that connects DC. And then the one that okay, this one just is listed all the weight on the table in ascending order. So here's very important, okay? Look at this part right here. Our graph has 4 vertices, so the minimum spanning tree, MST, stands for minimum spanning tree, will have 3 edges. It's always true. If your graph has 6 vertices, then you know your MST will have 5 edges. Okay, it's only 1 less edges compared to the number of vertices. If you have 6 vertices, 6 edges, meaning 1 is extra that you can get rid of. So since we have 4 vertices in this graph, I only need to keep 3 of them. We have 5 here, so whichever to make a loop and duplicate, I will get rid of it. So this is basically the algorithm, okay? If you understand it, well, slowly when you understand it, to find a minimum spanning tree, we will start from the smallest weight edge and keep selecting edge that does not form any circuit, doesn't form a circuit, okay, doesn't go back to its starting point with the previously selected edge. So let's see. 1 is the smallest weight, so we'll select that. 2 is the next smallest, so we'll select that. So we keep this one, keep AB, and then the next one, so it formed a circuit now because it's a circle, right? It went back to its original starting point, so we cannot keep that one. Next one up, DC, so we already have enough edges to connect all of the vertices. Okay, we got 4 vertices and 3 edges, and this is the smallest number of weight that we could possibly find. We don't need the last one. We don't need BD because if you keep that one, it not only make a circle, it's also a large weight. So we don't want that. So your minimum spanning tree value is the total weight you add together. 2 plus 1 plus 3. 2 plus 1 plus 3. Okay, so here's a video as a simple example. Does it give you a good idea what is minimum spanning tree? Just the introductory idea, you know. Are you guys still there? Here I have attached a link and examples, and you should go. You should click on those links and look at how the other example are working out. Okay. I don't have a lot of time to go through all the examples, but here's something that you can look at it yourself. So, this is what I have prepared for today. If you do you have any specific questions that you want me to go over?